Good afternoon and welcome to today's Machine Design webcast. Our topic today is Advanced Motion Control, Servo, and Step Motors, sponsored by Performance Motion Devices. I'm Bob Vavra with Endeavor's Design Engineering Group. To begin, let's talk about how you can participate in today's presentation. If you have any technical issues during our session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. We also welcome your questions during our event today, and we'll get to as many as we can during the Q&A session that will follow the main presentation, so feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Machine Design website within the next week. You'll be notified by email when the archive is ready. So let's meet this afternoon's speakers. Gaurav Shankran is Performance Motion Devices Vice President of Engineering and Strategy, responsible for future-proofing PMD and its customers who innovate in a fast-paced technological environment. And Ty Sofrino is the Chief Executive Officer and Chief Technical Officer at Trust Automation, Inc. Serving in that role, Ty oversees the company's strategy and direction that drives continued growth. You can learn more about our speakers by clicking on the blue speaker bio widget on your console toolbar. So gentlemen, good afternoon. We're looking forward to a great presentation.
Thank you.
Thank you.
Yeah, I would like to get this started. We wanted to try and cover this topic on advanced motion control, just to make it a little bit interesting. So just to see how Ty and a few of our other customers used closed-loop steppers, like do stepper motors for advanced motion. So just to get started, just a quick background on PMD. So we've sold over, we control over 6.5 million motors worldwide. And we've been innovating for the last 25 years. We have a pretty large OEMs and like Ty in defense and aerospace and stuff, and also in medical. So anywhere where you need precise motion, you tend to see PMD. And especially in this COVID setup, we've seen a lot of medical designs using PMD. So what we provide is a set of solutions that can go all the way across. So we do ICs and we do digital amplifiers, all encompassing digital drives and motion control boards. One of the keys of our products is the C motion language and APIs that can be translated from product to product. So it makes it a lot easier. Like Ty would talk about it. They start off a design with a motion board, and then when the volumes go up, they could transition to ICs or discrete devices. So typically that's what we've seen, where customers tend to stick with PMD because they've already done most of the software work and then transition from product to product. So just a quick look at our main value proposition. Obviously, we provide plug-and-play motion control, where motion control is not the key end solution. Like, for example, medical or defense, they're solving a bigger problem, and motion control is just a part of it. So we tend to be a value-added provider that helps them solve the motion problem, simplify the design. So as we talked about before, we kind of provide an end-to-end motion control framework that they can go from ICs to modules to boards. PMD is actually very well known for advanced motion controls, just S-curves, FOCs, full current loop. We work with the customer to solve the problem, to make it lower the vibration, make it quieter, just get better performance of whatever moves. And as you would hear from Ty, we tend to be very sticky with customers and tend to have long-term relationships with them. So with that, I'll hand over to Ty to kind of introduce Trust.
Thank you, Prab. Oops. So Trust Automation, I'm typically referred to myself as the chief bottle washer or janitor, but 30 odd years ago, started this company as a consulting firm, and And really that allowed us, and we've continued to do, we do a lot of engineering for other people that turn into products that we manufacture, but that allows us to touch on a lot of different industries. Motors are in a tremendous amount of industries, right? They're kind of intertwined in almost everything that you can buy and do, especially in the industrial space. So we have a lot of experience. It's a wide set of experience in that area. We've worked with PMD we're approaching 20 years now, and formed a good partnership with them, largely because it's a very compatible relationship. We tend to be a bit of a pain in asking for little extra things, and we can work with them to build some of that into what our needs are for our customers. Axes-wise, when I kind of break down our experience, we have 1 to 8 axis systems that we use the PMD chipsets in. Those go to 5 watt to 300 kilowatt solutions. Things above 10 kilowatt, 5 to 10 kilowatt, tend to be really incorporated as not just to controls or electronics like we're talking about here, but also all the electromechanical things that we tend to work on. And we do a lot of really integrated designs that are in a bunch of different industries. Our first products that we released over 20 years ago, approaching about 24 years ago, were Class AB linear amplifiers. We still produce a whole line of Class AB linear amplifiers, which are for ultra high precision. It's what we typically find in our semiconductor and some of our high-end, real sensitive noise signal medical customers where they can't handle the the PWM noise messing with their signals. But we also make far, far more digital drives now, and not as many digital drives that you would find on our website, but the high volumes are really customized designs that we build for specific things, and then many of those go into other applications. Again, high accuracy and then harsh environments. We do a lot of defense-related, aerospace-related, as Prab talked about. We also do a tremendous amount of semiconductor, industrial automation, and other types of things. So it's kind of all over the map. But when you drill down into the things that we make, somewhere in there's a motor and electronics. Just as a little overview of us, that's a picture of our new facility that we started modifying over a year and a half ago. It's our new manufacturing facility. We have a lot of Fortune 100 companies that we work with. And where this partnership forms with us is we don't just do a part. We have a lot of specialization with our engineering team, which is a big team. And we use a lot of really advanced tools, and it allows us to do some pretty heavy analysis. And then there's a whole lot of us what I refer to as graybeards that hang around and throw rocks at things, but we've been burned so much in life that we know what pitfalls to kind of watch out for. Electromechanical, I touched on that. We're a big electromechanical house. A lot of people in the semiconductor world think of us as an electronics house or a drive house, but we produce as much electromechanical mechanisms as the drive components to go with them in that space, as well as in other industries like aerospace, industrial automation, and others. It tends to be both the electronics and electromechanical pieces that go with it. And we do a lot of advanced machine control. We're doing a lot of weird things. We don't typically do the simple things. We do the hard things. There are days where I wish we just made lounge chairs or pizza ovens because I think I'd sleep better at night. But the reality is we do all kinds of stuff, and it's typically the really hard things. And then a big part of our relationship and our long-term relationship with our customers is not only are able to design things and help them out and design the glue in between, but we do all of the manufacturing, and we do the sustainability. We keep the long life. And Prab touched on that in his slide when he had a lower bullet point that talked about one of the ICs is still available from 1992, I believe it was. And as a company building things, our customer base, the people on this webinar, your goal is to minimize the end-of-life nightmares that everyone has to deal with on a regular basis, and we're no different. End-of-lifing of ICs, of components, is really hard on an engineering team, and working with PMD, where they keep these long, sustained lifetimes on their chipsets, just takes a few things off the table that you have to worry about, and that's very much appreciated.
Thanks, Ty, for the intro. So what we thought we would try to do is, obviously motion control has been around, like Ty talked about, he's been there 30 years, PMD has been around 25 years. We said, okay, what can we talk about that's something new and different? So we wanted to try and give a little bit of technical background on like a closed loop stepper, where you're trying to take the control techniques that you've learned from the brushless world and try and apply it to the stepper world. So that's what we want to try and cover in this webinar. So if you look at a closed loop stepper, the typical response is, oh, you put an encoder and you get a position, a predictive position out of it. But it goes far beyond it. So we call it closed loop stepper. I know Ty uses it in their designs. So it not only includes encoder feedback like it shows here, but it also has current control and FOC. And some of the big benefits you see, obviously the stepper motors are cheaper than the brushless. But with the closed loop stepper, you kind of get over some of the pitfalls, like lost steps, or you have less heat and better accuracy, and you get kind of a smoother, reduced noise kind of performance. Ty, do you want to add anything to this?
Yeah, if I could jump in. I think the key thing to look at this is there are many solutions that are a stepper motor with feedback that allows you to know if something went wrong, whether you got to the position you thought you were getting to, whether you slipped counts, things of that nature. And those are closed loop systems, but they're kind of blind systems. And then there's another classification of them where they don't treat the stepper motor like a true control system closed loop motor, and they do correction for the pulse engine that's putting the steps out to make the motor move, but it acts in a way that it can race or overrun if it runs into problems in the solution. It doesn't behave like a true brushless motor servo that so many of us are used to now. So there's these different levels of closed loop that people talk about. What PMD and this webinar is really focusing on, and what I've got some examples to talk about is truly running a stepper motor like it's a brushless permanent magnet motor with feedback, and overcoming the things that always plague that kind of a solution.
Yeah, so this is a little bit of eye candy. There's also a newsletter and a detailed article that goes into a lot more details. But what we want to try to highlight is, if you take a traditional stepper, you have the peaks and valleys, and it tends to be at the trough of the valley. That's where the steps go in, and then you get a little bit of oscillation around the step that it settles on, and that leads to noise and heat and stuff. So what we're trying to do is basically operate the stepper like a brushless at this operating point that's shown in red, with the encoder and position feedback, and kind of taking the FOC and treating it like a brushless motor, and doing all the adjustments that you would do with the traditional brushless, and trying to apply it to the stepper solution. So you can have like continually adjustable torque and phase angle and stuff. So it kind of gets you a better control setup at a lower price point. Yeah, and what we wanted to talk about also what we do apart from closing the position with encoder is we do this FOC current control, where we take, and it lends itself to getting higher speed and a more efficient operation where you're operating in the sweet spot. So Ty, do you want to add anything on this slide?
Yeah, I think you underplay the FOC part. So this is critical. Really, and I should take that back. This is a very important part, and I have a couple slides after this that talk about really small motors, and one of the applications we did. For small motor applications, the FOC component into this is really critical, and I'll go into that down below. But really, it's this combination of FOC and really a two-phase brushless motor, if you want to distill it down to what my 90-year-old parents would understand. and they may not even understand that because they have troubles with ATM machines. But really, it's a two-phase brushless motor, not a three-phase brushless motor. So that you have to do some interesting things there that PMD does really well. And then you put the FOC piece on top of that, and really, with all the mystery of FOC, when you distill it down into some simple things that people aren't familiar with it, there's these two terms they call the D and the Q term, and those are magical terms, but in reality, they're kind of a simple concept. The D term is this thing called direct term. And it's when, you have a coil around some steel and you have a tooth and you turn the coil on and the the magnet wants to line up with the tooth. And that's a direct pull. And that's what the D term is. So the D term is often thought about in a system is when you have too much direct D in a system, and it happens in a lot of systems for a lot of different reasons, really all you're doing is bending the shaft or preloading the bearings. And then the Q term is the quadrature term, and it's actually the turn that applies torque and is a rotational turn. And it's trying to keep the relationship between the magnets and where the coil is in this 90 electrical degree relationship so that you have the most optimum way of rotating a motor, not loading the bearings, not bending the shafts, things of that nature. So the FOC does this really cool thing in real time, cycle by cycle, to optimize how you're putting current into a motor and making it both quiet and efficient in the way of doing things.
Yeah, and actually, it's very interesting. You can actually hear it. You can hear the difference when it's turned on versus off in the line.
Well, you can also hear when you set up your D and Q wrong. It sounds really bad. Yeah. So just having FOC by itself doesn't fix anything. You got to have the FOC and you got to have your D and Q terms in the right place. Otherwise, yeah. It sounds really bad.
So Ty, do you want to go through this?
Yeah, I'll jump into these. So this is a little bit of what I was talking about. And in essence, our ability to create torque in a motor is a function of that length of the torque arm. So from where the magnetic field density is to where the permanent magnet is in a permanent magnet motor. And what you find in motors is if you can increase the pole count, you can increase the north-south number of poles in a motor, then you get motors which tend to be more RPM limited, but you get very good torque at lower speeds. So, like all things in engineering, the world's not kind to us. It likes to beat the snot out of us. So you never get something for nothing. So if you want really good high torque at low speeds, you tend to have to give up good, real high-speed operation as well from that same motor configuration or not. So there's a real good reason why, 20, 30,000, 40,000 or plus RPM motors are really two-pole motors. And it has to do with the speed at which you can calculate and push current through windings and things of that nature. But what we're talking about is how do you move slow and how do you do it with a lot of high torque? And that's where stepper motors have been amazing in this area because they were invented, and commonly used, I'll say, well before brushless permanent magnet motors and the control techniques for that, because there's simple mechanisms for them to be controlled. And that picture on the far right-hand side where it says hybrid stepper motor kind of shows this layout where there's all these little blue and darker colored points around the radius, and you're looking at just the south pole of that. There's a north pole buried on the other side. And it gives you a whole lot of those pole pairs that we're talking about. Whereas if you move over to the left of that just a little bit and you look at the three-phase permanent magnet motor, really that's what we would consider a four-pole motor. And for a traditional hybrid motor, they run 50 pole pairs, or 50 poles, 50 pole pairs, sorry. And on a traditional three-phase permanent magnet motor, they're going to be two pole pairs to maybe 4 or 5 pole pairs. It tends to be kind of the range. Well, there's a large order of magnitude different of low speed torque control between these two. And really being able to take a stepper motor, which is mass produced and very cost effective, and turn it into the performance that you get that is of a brushless permanent magnet motor and the smoothness associated with that. Because there's pitfalls with stepper motors when it comes to how you deal with them with holding torque with traditional drives, the torque ripple and the buzz that they have that Prab was talking about. Those are all things which have caused problems. When you can marry those two worlds together, you get this very cool, cost-effective solution that can do high torque at lower RPM ranges.
Yeah, and I think, Ty, when we were preparing for this, you were talking about all these unique applications and markets that end up using, not necessarily for the cost, but they end up using it for some of these benefits.
Yes, and there's a lot of industries where you end up either putting finer ball screws into the application to be able to get the RPM levels up in the permanent magnet brushless motors so that you can do the work that you're requiring, or they're really using the brushless motor in an area that it works decent at, but not as good as it could, because those applications never have to go that fast from an RPM standpoint. There's a lot of systems which don't go really quick, and they range. And if I want to take like the bizarro range of things that we've worked on, they go from these, if you see these 25-foot fans that go, in gyms and in airports and in, dairies and things of that nature. These are high pole count direct drive systems that are just coming online. Those maximum speeds of those motors may be 100 RPM, but they need a tremendous amount of torque. Versus, you go to the other end of the spectrum for the same thing, and you can have semiconductor applications where you're trying to move things very precisely, very smoothly. You don't want the torque ripple, but your RPMs are never very high because you can't afford those accelerations in a vacuum. Things will slip and move around. You can't do it. So regular brushless motors can be problematic in those areas where these solutions kind of can help you out. Another thing, just from a comparison standpoint, so I talked about how this works really well on small motors, stepper motors, and largely it comes down to, you take either of these motors, you got an EMA 8 and an EMA 11, and you can compare them there to a penny, and so they're small. And when you start thinking of the rotor size in each of these motors and the manufacturing tolerances you need, so you take one of these motors, you figure, the motor that is above the penny has a little over a 1/2 inch rotor core in it. That rotor core has 50 pole pairs inside of it. So you take 360 and you divide, which is, basically each pole pair is 7.2 degrees. You divide it by those 50 pole pairs, and then you divide that by 360 electrical degrees and say, I want a motor built to be accurate to within a degree so that I have good sinusoidal control of that motor in a traditional sense. And you're looking at a manufacturing tolerance to pull that off of the worst case manufacturing tolerance has to be 1/10,000th of an inch in these materials. And there's just no way you build motors like this to those tolerances. And this is an area where people tend to fall down and aren't happy with the results, because it's just not practical to build these motors to those levels of precision in a cost-effective way. So you step back to where the motors can be built in a cost-effective way, and you add the FOC control and the two-phase closed-loop control that PMD has, and now you actually can sway it to where these motors can actually, in many circumstances, behave in a way like a really good precision, much larger frame motor, but you get the torques you need in these small frames. And for this particular application that we were working on, we started with the NEMA 8 that's on the right-hand side of the penny. And, for torque reasons, we didn't have enough torque in that motor, on the second application. So the first application is using these motors. The second version of the machine, they needed more torque. And we had to fight to get to use the motor that's above the penny, the NEMA 11, because there was just such tight space constraints. So when you look at the fact that you can't just put a bigger motor in a lot of these applications, having the ability to do this tight control in these really small frames where the manufacturing tolerances kind of set you up for failure really from the beginning because of all the dimensions that have to be built inside, this was a really nice solution that allowed us to solve all of those problems.
Yeah, and Ty, you were talking about just if you look at the vibration part of it, you'd have to you could solve it in the electromechanical world with the way you build your machine. It's at a higher cost, or you just deploy these advanced controls at a small incremental cost that gets you to your end goal quicker.
There's a, so I'm going to offend probably half of the participants right now, and I apologize in advance for everyone who works for me at Trust Automation. My engineers, they'll know that they're used to this with me. But, there's an old joke that says, and this is often what happens in engineering projects, so I think everyone will recognize this, which is, how many, electrical engineers does it take to change a light bulb? And the answer is none. They'll fix it in software. And this is one of those scenarios where you actually can fix it in software. It's one of those magical things that has occurred where the other aspects of both the mechanical design and electrical design don't have to be superhuman to get there, because software actually can help really bridge the gap.
Yep.
One of my last slides, because I know we're kind of marching into the time frame, is just an example of one of the boards that we did for a semiconductor application. It's a 3-axis board, and we used 3 single-axis PMD chips for this. And the reason is they make 1 to 4 axis chips, but for this we needed really good current control. So we were able to get better current control from a single-axis chip. That has, we had limited things that we needed to do. We didn't need to do huge advanced coordination and things of that nature. So we were able to do those 3 axes, put our own host processor down. Our approach tends to be, we have our favorite ARM-based type TI processors that we use for host processors. They talk to PMD chipsets. We tend to sprinkle a handful of them around, and between our application engine and our libraries and working with the PMD side for trajectory algorithm control, and then marrying between the 2 companies at different times using different techniques for the drive side, we get the best of both worlds. And in this particular case, this is an EtherCAT controller. What was unique about it is it's a single EtherCAT slave point, but it's a multi-axis slave point, which you don't find out there. And even in the EtherCAT, definitions, when you go look, there's like 2 sentences that say, yes, you can do this, and they move on. So we were actually one of the first companies to actually do this multi-axis over a single slave EtherCAT node. Worked out really well because it allows us to do some customized homing and move routines without burdening our customer with having to do that on their application side and their whole piece of equipment. So it took some of that burden off of their engineers. It allowed us to specialize things down on our board. And it allows us to individually move all of the axes, align them, calibrate them, get them set up, and then flip into a mode where now they're all working in a coordinated way. And we can pop in and out of it, but they can also individually check. And it was just a neat, small solution that we were able to come up with for this particular customer.
Yeah, and I think the other thing PMD kind of provides is we are able to synchronize across a lot of axes. The largest we've seen done is like 100 axes machines. And they also have, we support something called user-defined profile mode, where you can load a table of a whole bunch of waypoints for robotics. And you can actually do the whole set of moves without any intervention, and then start on the next path. So it helps a lot in some of those advanced stuff where you're kind of offloading your processor, and the PMD chips can do them on their own.
And I would be very much at fault if when I was talking to the gentleman who designed this board just before this call to make sure I wasn't going to say anything dumb, he did bring up one of the things that he would like people to realize is PMD allows you with, so we have single turn absolute encoders that we put on the back of these motors. PMD allows you to pre-program a phase angle, which isn't commonly offered in this application. So it allows you to not have to go through some, weird, bizarre phase alignment algorithm initially when you start up to get your phase location to your pole location figured out. You can actually do that in a factory calibration. And then from that point on, you load it in when you fire up, you know where you are, you set your phase angles, and it allows a lot higher precision of these small motors when you can do a factory setup. And then, whenever the machine turns on, it's not someone trying to do a factory setup or the machine going through gymnastics. It's actually an absolute single turn encoder. You pop in the phase angle and away you go. You're going to be set as it was calibrated originally.
I think that was your last slide, right, Ty?
Yeah.
So we'll move to Bob for Q&A.
Well, great. Thanks, Prab. Thanks, Ty, for a great presentation. Got a lot of questions coming in. Continue to submit your questions by typing your question into the question window on the side of your screen and hit the submit button. And while we're answering your questions, please also complete the feedback form, which is located at the bottom of your screen. A number of questions came in during the presentation. We'll start with this one from Victor Gonzalez. Is the torque buzz and vibration reduced or eliminated thanks to the internal FOC current controls in stepper motors?
Want me to answer that one?
Sure, yeah, go for it.
Okay, all right. So I have a general thing that I tell. So the most precise thing that we've ever been involved with in a consortium with a company was in a company in Japan, and it's an accurate positioning system that's down a little bit south of 100. It's actually 90 picometer accuracy. So really, really tiny things. And then we do stuff for the military that if you're within, an eighth of an inch, you call it a win and everyone moves on with life. So we get this whole range of accuracy. So the reason why I'm leading up to that is when you get to really small or really high precision, everything is made of rubber and everything has torque ripple. It's about how you manage it. So for this particular application, the board that I showed and the motors I was showing, yes, we had extremely stringent torque requirements. We were able to, torque ripple requirements, we were able to pass all of those torque ripple requirements. But if you keep drilling down in precision levels, you're going to start seeing it again. So fortunately for this Acron, it was sub-micron, and we were able to reduce it to where we didn't see the sub-micron disturbances. But if you were to go down into the, let's say, 25 nanometer or smaller range, it would probably start showing back up again, and you'd need to switch to a different technology.
Very good. Timothy Rosario is asking, what types of applications are using these lower RPM, higher torque steppers? Well,
Rob, I tend to talk too much. I'll just throw that out there. Do you have anything you want to say on that, or do you want me to jump in? Nope, I'll jump in. On these applications, where we typically see it is we see systems that want to move really slowly are handling something that's not captured, so it can slide off if the speeds are too high, or it's a lifting system where you're overcoming, in the semiconductor world, you're overcoming a vacuum force that's really high. And it tends to be, again, you're moving something up and down, you're working against gravity. Gravity is what's holding the thing in place. Vibrations tend to move things, skitter them around. But the low speeds you need to have these very gentle accelerations, deaccelerations, these very gentle motions, which tend to all be very low RPMs to do that. And the high RPM component of the motor is kind of a waste, in that scenario. There are other applications like the fan we're talking about, testing equipment we've worked on where you're driving coupons and samples across the surface, and there's a controlled, high torque, low speed type operation of doing a test process, tending to be in the worst places that brushless motors tend to work, that you can kind of see advantages from this.
Very good. This one from Beryl Axoy. What's the maximum number of axes, I guess, because that can be controlled by one IC chip?
Yeah, I think, so we actually do a wide range. So we have a 4-axis single chip solution. It's a 2-chip setup. Or we have single axes that can be ganged together. So it depends on your application. So typically, for 4 axes, they tend to do this chipset, which is a controller chip and an I/O chip. And for odd number of axes, they tend to go with the single axis solutions. But the nice part is you can actually synchronize across lots of axes. So they end up, depending on their layout, they tend to pick one or the other. And we also do amplifiers that plug in, that interface seamlessly with these chips. So you can build your whole board using PMD ICs and amplifiers. And I know a lot of customers start with a board, a Prodigy motion board that we provide. And then if the volumes go up, they tend to design their own card. So we kind of give them a path forward.
Very good. I think we've got time for one more question here, and that is from Dan Hunter, and I hope I'm asking this correctly. Can you evaluate the slow speed torque ripple without characterizing the harmonics of the step motor?
Well, okay, how do you answer that? So yes, you can absolutely characterize it because it's a measurable entity that's separate from the harmonics of the step motor. What you end up with is when you combine those two analyses, you start to find where the problem actually is. Is it in the internals of the motor configuration and its pole pair manufacturing setup? Or is it a function of your feedback and how it's aligned to the poles, or the density of the feedback? Is it a low resolution feedback? Is it a high resolution feedback? And how does it pair it up with the internals of the motor? Or is it an outside influence, which we run into? I have a general statement which I state, which is there's knowledge and there's wisdom. Knowledge you get from a book, wisdom you get from making mistakes. So we have lots of wisdom in this area where you have an external influence, either electrically or mechanically, that starts to show up in the system. Stick slips in ball screws or in the mechanism, the rail mechanism, things of that nature. So the answer is yes, you can evaluate the torque ripple characteristic outside of the harmonics of the stepper motor, but it's really a combination of several of those things.
Very good. Well, that's about all the time we have for questions here today. I want to thank Ty and Prop for a great presentation. If we didn't get to one of your questions, we will be in contact with you offline to get all those questions answered. So that concludes our presentation for this afternoon. On behalf of Machine Design, I'd like to thank Performance Motion Devices for sponsoring today's event, and thanks to all of you for joining us. Have a great rest of your day and stay safe out there.
Thank you.
Thanks, everybody.